A race engineer watches brake pressure traces while a car enters turn 1 at nearly 200 miles an hour. A pipeline operator monitors vibration levels on a remote pump station hundreds of miles away. On a rocket engine test stand, engineers watch chamber pressure during ignition, looking for signs that combustion is becoming unstable before hardware destroys itself. Different machines, different industries, same problem. How do you measure what is happening inside a machine accurately enough to trust the number? Because before telemetry can be transmitted, displayed, analyzed, or acted on, something has to happen first. The machine has to measure itself and the conditions around it. Pressure, temperature, vibration, position, flow, power. All of it begins as a physical condition in the real world. And turning those physical conditions into trustworthy digital measurements is the job of instrumentation. I spent much of my career working with aerospace telemetry systems. In this series, I want to explain the basics of how telemetry systems work in plain, practical language. In the first video, we used Artemis II to introduce the overall telemetry chain. In this episode, we zoom into the beginning of that chain. Sensors, signal conditioning, data acquisition systems, analog to digital conversion, and how real machines turn physical behavior into digital data engineers can actually use. Why measurement comes first. Most people think of telemetry as communication. Radio links, screens, graphs, data flowing into a control room. But telemetry actually starts much earlier than that. It starts the moment a machine tries to measure itself. A rocket engine does not know its chamber pressure unless something measures it. A race car does not know wheel speed, brake pressure, or tire temperature unless sensors are continuously watching those systems. A remote industrial pump station does not know a bearing is beginning to fail unless vibration sensors detect the change early enough for someone to respond. Before there are graphs, displays, or alarms, there is measurement. And modern machines measure far more than most people realize. A modern racing vehicle may monitor suspension loads, steering position, brake pressure, wheel speed, tire temperatures, fuel pressure, battery voltage, and acceleration all at the same time. An industrial facility may monitor pressure, flow, tank level, motor load, vibration, temperature, and electrical power continuously for months or years. A rocket test stand may monitor hundreds or even thousands of channels during a single engine firing. Because once a machine becomes too fast, too remote, too dangerous, or too complex to understand directly, instrumentation becomes the only practical way to know what is happening. So how does a physical event become telemetry data? Usually through a chain that looks something like this. Physical condition, sensor, signal conditioning, data acquisition, analog to digital conversion, digital measurement. Take something simple like pressure inside a pipe. The pressure itself is a physical condition. You cannot transmit pressure directly through a telemetry system. First, a sensor has to convert that pressure into an electrical signal. That signal may be extremely small. It may contain electrical noise. It may travel through long cables in a harsh industrial environment. So before the system trusts the signal, it often passes through signal conditioning hardware designed to clean it up, protect it, scale it properly, and prepare it for measurement. Then the data acquisition system collects the signal. Finally, the analog to digital converter samples it and turns it into numbers. At that point, the pressure inside the pipe has become digital data. Now it can be logged, displayed, transmitted, analyzed, or used for automatic decisions. And this is where an important distinction appears. Data logging and telemetry are related, but they are not exactly the same thing. Data logging means storing measurements for later review. Telemetry means sending measurements somewhere else, often in near real time. Most real systems do both. A race engineer may review full log data after the session while simultaneously monitoring a smaller set of live telemetry channels during the run itself. The measurements may be the same, the purpose is different. What real sensors measure? Sensors are not measuring data. They are measuring physical behavior. Pressure sensors may monitor hydraulic systems, fuel systems, combustion chambers, pipelines, or cooling systems. Temperature sensors may monitor engines, bearings, electronics, exhaust systems, batteries, or cryogenic propellants. Vibration and acceleration sensors often exist because machines rarely fail instantly. A worn bearing, an unbalanced shaft, or structural fatigue usually appears first as a small change long before catastrophic failure happens. Position and speed sensors track things like valve position, wheel speed, actuator movement, shaft rotation, or steering angle. Flow and level sensors monitor fuel flow, coolant flow, tank levels, or industrial process systems. Force, strain, and load sensors measure structural stress, suspension loads, thrust loads, or mechanical forces acting on a system. And power-related measurements, voltage, current, and power consumption, help operators understand whether systems are operating normally, overloaded, or failing. What matters is not just the measurement itself. What matters is why the measurement exists. Every sensor in a telemetry system exists because somebody decided that condition mattered enough to monitor continuously. The hardware itself is not mysterious. In the real world, sensors are physical parts mounted to machines, threaded into pressure lines, clamped to structures, bonded to surfaces, bolted near bearings, or wired into power systems. They may be small, but they are part of the machine. That hardware also has to survive the environment around it. Heat, vibration, moisture, pressure, electrical noise, and years of continuous operation. A measurement is only useful if the device making it can keep working where the machine actually lives. The packaging changes from one machine to another, but the engineering problem is the same. A race car, a remote pump, and a rocket test stand all need a way to turn hidden physical behavior into reliable measurements the system can use. So before transmission, displays, or decisions, the first challenge is measurement quality. Detect the condition, protect the signal, convert it into reliable data, and make sure the number can be trusted. One thing surprises many people when they first work with instrumentation systems. The sensor signal itself is often messy. Some sensors produce extremely small electrical signals. Some signals are noisy. Some travel long distances through electrically harsh environments. Some sensors require external excitation power before they work properly at all. A strain gauge measuring structural load may produce a signal so small it must be amplified before the data acquisition system can reliably measure it. A thermocouple measuring exhaust temperature may require specialized conditioning before the signal becomes useful. An industrial sensor mounted hundreds of feet away from the control system may need protection against electrical interference, voltage spikes, or grounding problems. This is why signal conditioning exists. Signal conditioning helps filter noise, amplify weak signals, isolate circuits, scale signals properly, and prepare them for reliable measurement. Because the telemetry system cannot make good decisions from bad measurements. And by the time engineers see numbers on a screen, a tremendous amount of invisible work may already have happened just to make those numbers trustworthy. Once the signals are prepared, the data acquisition system takes over. The data acquisition system becomes the collection point for all of these measurements. It gathers signals from sensors throughout the machine and organizes them into channels the system can process. Then comes one of the most important transitions in the telemetry chain: analog to digital conversion. Real-world signals are usually analog. They change continuously. But computers, displays, recorders, and telemetry systems work with digital values. So the analog to digital converter repeatedly samples the signal and converts those measurements into numbers. Pressure becomes PSI or bar. Temperature becomes degrees. Voltage becomes volts. Acceleration becomes digital values engineers can graph, monitor, and analyze. Some measurements may only need occasional updates. Others may need extremely fast sampling. A slowly changing tank level may not require much bandwidth at all, but vibration, acceleration, combustion instability, or shock events may require sampling hundreds or thousands of times per second to capture what is really happening. Because if the sampling is too slow, the system may completely miss important behavior. Modern telemetry systems often monitor large numbers of sensors simultaneously, but not every sensor gets its own dedicated converter. In many systems, a multiplexer acts like a very fast electronic selector switch. The data acquisition system rapidly scans through channels one at a time, measuring each signal in sequence. Done fast enough, the system builds a complete picture of what the machine is doing across many channels. But this introduces another engineering decision. How often should each channel be measured? Not every signal changes at the same speed. Battery voltage changes relatively slowly. Tank level may change slowly. Temperature often changes gradually, but acceleration and vibration can change extremely quickly. A rocket engine ignition event may develop dangerous instability in fractions of a second. A race car suspension impact may happen almost instantly. So engineers choose sample rates based on how fast the real-world condition can change and how important that information is to the system. And this is where telemetry starts becoming a balancing act between measurement quality, bandwidth, storage, processing power, and engineering priorities. By the time telemetry data reaches a screen, one of the most important questions has already been answered. Did we measure the real condition accurately enough to trust the number? Because telemetry does not begin with transmission. It begins with instrumentation. Good sensors, good signal conditioning, good sampling decisions, good data acquisition. A perfectly transmitted bad measurement is still a bad measurement. And as telemetry systems become more important in aerospace, industrial automation, robotics, motorsports, and remote operations, the quality of those measurements matters more and more. Once measurements become digital data, industries use standards and common practices to handle timing, formatting, recording, transmission, synchronization, and interoperability. We will come back to those later in the series. But everything starts here, with measurement. Because before a machine can report what is happening inside itself, it first has to know. In the next episode, we will follow those digital measurements to the next step, how telemetry data is organized, formatted, timed, and prepared to move through the rest of the system. If this was useful, please like the video and subscribe to ARH Tech Lab for the rest of the Telemetry Data Flow series.